I welcome all of you on the platform of YourPedia Education. And as you know, Team YourPedia has covered first ever research and development fair, which was held in IIT Delhi on October 14 and 15, 2022. In that fair, 23 IITs participated, and professors of IIT came out with their projects, latest projects they were handling, and they demonstrated, technology and new breakthroughs in the technology. This particular video is related to the interaction with Professor Deepak Gupta. He's from IIT Kanpur, and Professor Gupta's one of the projects was displayed in that particular trade, that particular R&D fair. That is low cost anti-counterfeiting labels. Professor Gupta is authority on many domains, on many field of research. Professor Gupta has done marvelous work in the field of organic electronics, flexible electronics, semiconductors, thin film transistors, modeling and simulation of materials, and he's a thoroughly knowledgeable individual in his domain. He's also handling many centers and working very closely with the government of India also to basically implement those things, whatever things are being discovered or whatever devices are being made, to implement it so that it is used for benefit of the people at large. So today my interaction is with Professor Gupta. So let's go and listen to what Professor Gupta is to say. Thanks a lot, Professor Deepak Gupta, for your time you spared for me today, and welcome on YourPedia Education.
Thank you, Vijay, for having me here.
Okay, Professor Gupta, you are an authority in the various fields of electronics, especially if I mention organic electronics, flexible electronics, semiconductors. You have done marvelous work, sir, in the field of thin film transistors and modeling and simulation of materials. And Professor Gupta, recently one of your projects, low cost anti-counterfeiting labels, that was projected in first ever R&D fair, which was held in IIT Delhi, sir, on 14th and 15th of October 2022. So we happened to visit the project, sir, and this entire interaction is related to your domain of specialization and about this particular project. So may I ask you to initiate this particular thing, sir? Can I start the interaction points which I have collected?
Absolutely, absolutely.
Yeah. So, Professor Gupta, first I would like you to tell us about the scope of material science in present world. We know so many things, we hear about material science, but it's an interdisciplinary domain. I mean, from different branch of knowledge, people, they go for material science. Sir, आप इसका scope हमें बताइए कि what is the scope of material science?
So, three interdisciplinary word you use. Frankly speaking, I don't find it interdisciplinary, or I find it interdisciplinary based on what is not interdisciplinary.
Okay.
Everything is. If you take electrical engineering, there is a power systems also. There are electronics. There is communication. There is networking. People in computer science also deal with many of those things. Mechanical engineering deal with that, etc. So everything, as far as products are concerned, they are utility to human beings.
Right.
So they are always interdisciplinary.
Right.
Education is by discipline, and in that, material science and engineering stands on its own, including the metallurgy and the whole thing. Right. So now you said the scope. Scope is okay. So I'll tell you the way I think about, and I am not going to give you a routine answer which everybody says that it is underlying thing between this. Those are known to everyone. So let's talk about what it means.
Right.
Note, as a consumer, as a society, we see gizmos,
Right.
gadgets.
Right, sir.
Gadgets is what we touch and feel, not the material.
Right, sir.
If you look at material as a product itself, then you can name maybe copper, iron, steel. Those are sold as metal themselves.
Mm-hmm.
Those are product. But if you remove that, then after that, if you remove that, then really materials go into making a product.
Right.
What happens therefore is, take examples. I'll give you example. You take LED, for example, white LED.
Right.
Now notice, when did the society became aware of white LEDs? White LEDs came sometimes in late 2010, around that time frame. Whereas the blue LED, bright LED, we were waiting for, came out in 1995. And in 1997, I started talking to Government of India that, look, this is the technology which is about to come.
Right.
Right. Point I'm trying to make is, material science people work ahead of the when world comes to know about it.
Yes.
What they do then becomes the technology. The technologies are built on top of it,
Right,
and
sir.
material needs are satisfied to give that output which is being desired.
Right, sir.
This is the positive part. The negative part is once that part is over, then R&D and all that stuff is over, then still material science continues to go, but the role becomes much lesser.
Right.
And a mobile phone which consumer holds in his hand, then that becomes a lot more lucrative and interesting. And that's the reality of life.
Right.
That science is one step away from the consumer.
Right, sir.
Except for things such as steel and iron and that kind of thing. So scope wise, it is an essential thing. Anything you want to do,
Right.
material science has to come in. Just that we come typically way early before the society sees that product.
Sir, we talk today about self-reliant in becoming self-reliant in different domains. आत्मनिर्भर हम बनना चाहते हैं. So I want to ask you, sir, how far in the field of material science you think we are as of now self-reliant, and how we can become if we are not?
That's a difficult question. I mean,
Okay.
probably it goes beyond my knowledge. So I will keep the answer very short in this. We are not going to become self-reliant in materials because we don't have many materials.
Okay.
So many rare earths, lithium, even silicon. The sources of silicon and commercial sources of silicon. Silicon is a lot in India. So many things we will never become Atmanirbhar because we don't have it.
Yes.
And many things we have, but we haven't done good job of producing them at lower cost than outside, than the imports. Right. Yes, the work continues on it, but more importantly, materials Atmanirbharta comes more from point of view of when a product is defined, even in defense, for example, you want to try engine, then what kind of blades, what etc. Those kind of developments happen, and even that we are not Atmanirbhar, but slowly the progress is happening. I do not know as much to answer your question.
So very, very honest and candid answer, sir. Very honest answer from your side. And yes, there are many domains in which India is still to catch up. Professor Deepak, I was going through your profile, sir, academic profile, and I found that you've done your graduation in metallurgical engineering from IIT Kanpur. Then you've done MS in material science from University of Florida, and PhD in material science from University of California. I find that presently, sir, you are contributing a lot in the field of electronics, as I mentioned, organic electronics, flexible electronics. So you are also working in semiconductor domains and all. Please tell us something that how this trajectory, I mean, your academic trajectory, how it evolved that way.
So simply, I was a student at IIT Kanpur back in 83 to 87, did my BTech in metallurgical engineering. And it is the same department which has expanded its scope beyond metals into other materials, into electronics and optical and magnetic, other materials. Hence, my trajectory and the departments around the world who got used to metallurgical engineering became materials also. So that's a natural thing. I actually was working on more traditional materials, except I took a job in US after finishing my PhD in Motorola and semiconductor fabs in the processing side. So I started looking at after the processing across the board is similar. So started doing processing of semiconductor chips, and that's how I got into it. Then I started doing some little device level design, not circuit level, device level design. And after spending 4 years, then came back to IIT Kanpur. So then started thinking that what I have learned, let me start that new field. And opportunity arose with the company Samtel, which used to make color picture tubes, and actually got into displays. So what you may not know is that we made for Samtel with a Samtel team in IIT Kanpur in 2007. We had the first OLED display, which by 2010 was meeting all the commercial specifications. Okay, to plug it into a mobile phone, and it would work, and it was meeting all the lifetime testing and everything. It was it never got commercialized, but those days for feature phones used to be there, not the smartphones. Feature phones used to be there those days, and the display was for that. Okay, and full color display made in IIT Kanpur with commercial specifications. So that's how we started, and started on LEDs. I mentioned to you when I came back from here, we thought, what are the things we do? We knew about this LED coming. 97, I came back to and joined IIT. And 95, I told you, the invention happened, for which finally a Nobel Prize was given. By the way, I don't know how many times else for Nobel Prize was given to an engineer who, at the time of invention, had only a master's degree.
Okay.
The blue LED, bright blue LED, and you notice the blue LED was missing. You take the blue LED and put yellow phosphor on it. So part of the blue light comes out and part blue light gets converted into yellow. They mix and they give you white light.
Okay.
That's what you see in your homes today.
That's true.
That became possible in 95, and the moment 95 it happened, everyone in material science domain predicted that now white light is coming, LED white light is coming.
Okay.
So started working some little bit LED and gallium nitride also. Then moved on to then another discovery which was in organic electronics about conduction in plastic. You think of but there was a discovery of conducting polymers. We started working on that area in 1998, and voila, in 2000, Nobel Prize was given for that discovery.
Okay.
So
Okay.
we started working before that on it to make out of it.
Okay, Professor Gupta, one more question I would like to ask you, though it is a little deviation from my script. That is, Professor, you graduated from IIT Kanpur long back, and then you went to US when there was going to be a boom in these areas in which you were working that time. So you graduated from, you did your master's and PhD from the top universities, and you even entered the corporate world with one of the best companies you were working, best technologies you were working, and they were at that time, most transformational in the field of research. Why at the first place you decided to come back to India, and how do you see that decision today?
For this, I give a very standard answer. Okay. So let me ask you, Dr. Vijayan Singh, I assume you are married?
Yeah, I'm married, sir.
So when you come back home, does your wife ask you, why did you come home?
No.
I came home, why this question should be asked to me?
Okay.
I was born here, this is my home, I came back home.
Yeah,
that question should be asked to people, those who do not
yeah. Not now.
Standard answer.
Yeah. Normally, sir, why actually I asked you this question, because nowadays there are so many youngsters who go abroad and they are in that stage of confusion at this stage of their life. So maybe, the answer from people like you, maybe a light showing a thing for them and all. That's the reason I asked.
Home is always home.
Yeah,
I am no hyper nationalist. I am not a hyper nationalist. Yes. No, I will not say I love my motherland. That's why I came back. No, I love who I am. I love people here. I love life here. That's it.
As I earlier said, very honest answer, sir, from your side for this question also. So now I come to main project, Professor, before we go forward and I discuss more things about your research area, sir. I would like you to tell us about the project which was displayed in R&D fair in IIT Delhi, low cost anti-counterfeiting labels. So please tell us something about this project, sir.
Yeah, so we started in, as I said, National Center for Flexible Electronics in IIT Kanpur started in 2014, and in 2013 when we were proposing it, at that time I started thinking about anti-counterfeiting, and this was a concern, in terms of medicines, in terms of agricultural products, where farmer is a marginal entity. Economic status is marginal. One crop loss, and that's it. I lose 10,000 rupees. It's not a big deal, but a farmer losing 10,000 rupees is a big deal if his crop is lost. So farmers and this medicines and food and all that, in our country there's so much counterfeit, fake products available. If it's a fake toy, okay, I don't so much care. But when it concerns your health, your life, then and livelihood, then it becomes an issue. So that used to bother me. So when National Center for Flexible Electronics was starting, we consciously put anti-counterfeiting as one of the research areas in the center. 2013, we started looking into what kind of electronics we can build in, so that the people who are buying things can check whether something is genuine or fake.
Right, sir.
Now, when we started looking at it, and we considered several options. When we started looking at several options, we realized that putting electronics on each package then would start making it very expensive. In our estimate, it would have costed upwards of 10 rupees. Not only that, for verifying on the street, you would have had to have a special device, and then you would have to verify using that. So then we realized that this is not going to work. So then we decided, okay, the way we have to approach is that the physical feature which is affixed to the product must be really inexpensive, and all the electronic function we should bring it to the mobile phone. And mobile phone is ubiquitous and everybody is having in their hand these days. And smartphones are getting popular day by day.
Right, sir.
So we start looking at, okay, if that is the case, then for a smartphone, what are the means by which a smartphone interacts with anything outside? Now, it interacts through a keyboard meaning where you can punch numbers. It interacts through sound. It interacts through its camera, and it interacts through your touch screen that you can touch. So touch is how you can interact with it. By typing keys, you can interact with it. With sound, you can interact with it. With camera, you can interact with it.
Right, sir.
These are the 4 ways you typically interact with a mobile phone.
Right,
so we said, okay, if that is the case, then we have to do with anti-counterfeiting with one of these functions.
Okay.
And that's how we narrowed it down. We said, let's make it optical, visual, so that people also see it. Right? People also see it, there is something to be done. And that's how we said, okay, camera and the tag is what we need to have. And then we went about designing it.
Okay.
I can give a long answer, but if you have a follow-up question on it,
Yes,
how this technology works, then I'll wait until you ask that question.
Yes, sir. Actually, my next question was related to this only, Professor Gupta. This question was related to National Center for Flexible Electronics. When was this created? What was the need we felt of creating it? And what is the flexible electronics? My question was that only. So though partially you answered, but I want again, sir, if simplified, if you can explain.
Absolutely. So in IIT Kanpur, we thought that technologies such as silicon now are in tertiary domain. That means they're so well established. It is very difficult for a new player to come in.
Right.
Start from scratch. But because those who are ahead are way ahead. Right.
Right.
So that is why we started. And I mentioned LED to you. I mentioned displays to you.
Right, sir.
We felt that it is our job to sensitize the government that this is about to happen in 10 years.
Okay.
So start early now so that you don't miss the same boat which we missed in 60s on silicon.
Yes.
Right. So start early.
Right.
That was the idea. So then we advised about LEDs, and I talked about LEDs.
Right.
Then we decided displays. We said, look, India is self-reliant, or at least 40% of, or maybe 60-70% of picture tubes of the TV, the CRT television, which you and I have seen quite a bit. Young generation would not have seen it that as much. That were made in India, entirely made in India, right? And we were advising that, look, flat panel displays are about to come, and they will destroy our industry. Which is what happened.
Right.
And now course correction is going on. It is the same. Then when it came in 2000, so this we have been doing, had been doing this. When it came in 2013-14 time frame, we said now we should actually put up a whole center. Other than advising merely, we should translate into an action. So we said, okay, flexible electronics is another thing that is going to come. Okay. And so therefore we saw that future, and we said, okay, this time let us set up a center which interacts with industry. So this is a very focused center wherein about maybe 50 to 100 people, 50-60 people are working, who in IIT Kanpur are employed on project and on permanent positions to work with industry only. They have no other responsibility. Okay. And 8-10 of us and our students are the one who are from IIT Kanpur academic side. Okay. We provide the academic input, and then the products are made in the center with a dedicated staff which works with industry. And the center has a model of membership with the industry and many partners, and we take up a project only when we have an industry partner by and large. So we do something other things also. So that's the kind of center we built, and that's what we propose to basically government, and say we should have such a center, because this is yet another technology which should come in maybe 10-15 years.
Right. So it looks like typical example of industry academia interaction, sir, and maybe the concurrent engineering which we are using presently there.
Yes, I would like to say something else also here. Academia industry interaction again is a little bit hollow word. Everybody uses it, but its implication is not very clear. So I'll try to explain that. Okay. Now I will explain in terms of what is called as technology readiness level, TRL levels. Okay. TRLs used are for different. Europe uses different, US uses different people use different, but does not matter. It's something on a scale of 1 to 10. Okay. Without going into specifics of it. Right. Typically, academia deals with taking their ideas to TRL level 1 or 2. Okay. Those who are very industry oriented academia people, they take it to even 3 and 4. Okay. That's where most academia, even industry-oriented academia will stop.
Okay.
TRL level 7 and 8
Okay.
are somewhere where industry starts accepting it.
Okay.
Okay, they start accepting it, that maybe they can get into it and they can use it. Academia thinks that when they've taken it to level 4, that it is ready to go to industry.
Okay.
Industry thinks that, look, there's a lot to be done in between, and I can't take it at this risk at this point of time, right? And both parties think that, one says it is not ready yet, good idea, but not ready yet.
Okay.
And tells academia to work longer, more on it. And academia thinks I've done everything I should have done. Now I have other interest to do, take care of. So now it should go to industry.
Okay.
This region in between, called TRL 5 to 7 or something in between 4 to 7, is what is called as value of death.
Okay.
This is where most technologies die.
Okay.
This is where most technologies die. Academia people also don't want to do it. Is boring. And industry people also don't want to get into it. It's too risky for them.
Okay.
Okay. So we pitched our National Center for Flexible Electronics in this region.
Okay.
That we will do projects which are TRL 4 to 7.
Okay.
So that's the value of death we are putting our center in. And that's when industry and academia interaction happens.
Okay. So, Professor, you take it to the next level of TR, as you said, 7 to 8, where it gets acceptance of industry?
Absolutely. That is the mandate.
Okay. So, how successful are you in taking all of the projects which you take at lower level of TR? How many of that goes to 7, 8 level? All of them?
There are lots of products which have come out of IIT Kanpur from this National Center for Flexible Electronics and getting commercial. I'll name some to you. Glass can always be seen as a half full or half empty. Seeing it as a full side I'm talking about. There's a jacket we have made which has a printed heaters inside and runs on a power bank meant for our defense forces on the borders where it gets cold. So it supplements their coat, and they can wear lighter coats.
Okay.
Certain heat is maintained through these devices. This is now going to production level. There's another company which is formed, Licotronics. We have made simple printed electronics circuits for teaching children from 8th to 12th grade. You do physics labs, physics lab in your, and then you use breadboard, you use resistors and diodes and all that stuff. That's printed already. And we have generated a pen in which we have filled silver ink. And then you write that with the silver ink. It is a metal conducting ink. Okay. And then you join it, and you can make circuits and then test. Right. So that's a product which is found. There is some detector for breast cancer. There is a level sensor for IV bottles. Level keeps falling down, and you don't know when it is empty. Then somebody has to call the nurse to change it. So we have made an electronic function to sense when it is getting empty. These are something top of the head which I'm remembering. So there are about 10 or 15 such technologies which have come out.
So, Professor, looks like you have already identified and found the solution to one of the major problem which our academic institutes are suffering from. So why can't we emulate the same thing which you have done in other institutes? Are people following this kind of approach somewhere else also?
People have tried different things, different models, and we try to go and organize lots of meetings, road shows with industry. But perhaps we have done a lot more on the industry side than we have done on the academic interaction. But industry, we go on road shows, different cities, and try to get industry. Perhaps we could do more on the academic side also.
Okay, Professor, my next question to you is related to the shortcomings of traditional anti-counterfeiting technologies such as hologram, QR codes, UV sensitive inks, etc.
Okay, this is very, very important subject, and I would like to share a screen. So first of all, okay, before I say that, I'll take a little bit time in answering this question.
Yes.
And I want to say that you cannot think in terms of anti-counterfeiting technology as a technology. And you can't say that I will have this technology, I'll replace it with this technology. That is never going to work, and it has never worked. You have to understand, why does counterfeiting happen? What are the fears of those guys? What they don't fear? And hence, what should be the technology?
Yes.
So first of all, let me try to explain through. Let me share my. If you will allow me to share my screen.
Yes, sir. You can.
Okay. So let me see if I can
It is visible.
share my screen here.
Yes.
So here it is. First, everybody needs to understand there is a difference between traceability and authentication.
Right, sir.
Okay. Traceability means honesty is assumed that product is not fake. You're just going through where is it today,
right,
and how it is moving around and what is the journey it had. That's the traceability part. Why are you interested in it? You may be interested in it, or brand may be interested in it because it wants to do supply chain management. It wants to see where the stock is, where the stock is not moving, where it is moving fast, where it's going down so that they can replenish it. That kind of management system traceability can bring in, but it cannot bring in authentication at all.
Yes.
So I will come to QR codes. QR codes which are meant for traceability, but not for automation. Traceability and automation and traceability. They cannot provide any authentication. And similarly, holograms also, which I'll try to explain through the next slide. This slide is where I want to spend time and explain to you what the philosophy is. We first developed a philosophy, and only then we decided to develop a technology. What is that? Let me ask you a question. That if you see a hologram pasted somewhere, or if you see a QR code for authentication, QR codes for payment gateways, that's okay. That's people are paying through it. That's okay. They're scanning it. It takes you to a certain link and you pay. That's a link only automated form of link. But for authentication, wherever it has been provided, holograms and QR codes, ask yourself how often have you checked it?
Very less.
You don't check it, right?
Yeah.
You don't check it. Fine. I will skip the second point. I will come back to it later. Now look at the supply chain of a fake manufacturer. Fake products. There is a manufacturer who makes fake products. Who is this manufacturer? This manufacturer is like you and me, a middle class person. He is not a really ultra rich guy.
Right.
If a brand makes 10 lakh pieces of something in a month, then this guy makes in a Kanpur city only 1,000 of them. It's a distributed manufacturing. Somebody makes it Meerut, somebody makes it Noida, somebody in Bombay, somebody in Delhi, somebody in Jalandhar. They make this 1,000 pieces, right? And so they are not ultra rich people, but they are illegitimate business owner. They operate from the basement of the house or rooftop or whatever. It's very difficult to catch them. Occasionally, when they are caught, it's a newspaper report. Raid was conducted and something was found. The fact that it appeared in newspaper tells you that it is a rare event, right? Now, suppose I am the fake manufacturer. If I've made it, how do I sell it? I have no means to sell it. I sell it to the consumer. I have no reach to the consumer. So what do? I go to a retailer and I make a deal with retailer. Retailer always knows what he's doing. So that he's selling fakes. But he makes a deal because there's a financial benefit. So question is, retailer is a legitimate business owner, registered, and he's in the marketplace. He's open in the open. He's selling in the open. The question is, I compare with crime of passion. Crime of passion is irrational crime done in heat of moment. Financial crime obviously is done for financial gain, as the name suggests. But there's a very important thing. It's a very rational crime. When does one commit a financial crime? When they think that they will not get caught. That's the very important point. That financial crime is only committed when the risk of getting caught is negligible. Now you get back to the holograms and QR codes and holograms have been around. Obviously, still this retailer is selling it. Then you have to understand he does not fear them, and you'll understand why he does not fear them. Now, the consumer behavior. Consumer behavior is that they are not going to check.
Yes.
So unlikely that many consumers will ever check. But does the retailer know who will check? He does not know. If one out of 100 checks, he does not know who that person is. Now, if you put power in hands of consumer, inspectors, retailers alike to check it, and there's no option to deny that something was fake, then 1 in 100 is good enough. The technology should be such. That's now look at the second point I have made here. That if a copied QR code is pasted on a container, on a fake container, or hologram, which is not even exact replica, which you can make exact replica, but even if it is approximate hologram, you stick it there on the fake, Now, what do you do for the hologram? When you look at a hologram, you think the hologram is stuck there, so you think it must be authentic. You buy it, right? But this fake guy also puts a hologram. So in fact, fake product, you think it is authentic. Holograms therefore play a negative role. And QR codes are copied, and they paste the copied QR code also there. Once the QR code copied is pasted, you scan it, it'll give you the same answer as a genuine one. So therefore, once it is pasted, the retailer has perfect deniability that how would I know that these are fake? Even if you catch it, even if a brand inspector comes there and says that, look, I know my product, this product is fake. He says, oh, maybe you are saying it may be fake, but what do? I do not know. This is an escape route. And that is why he does not fear holograms and QR codes and similar hidden features. Anyway, he does not know. If your UV ink is hidden feature, if UV ink, then the people who know the brand, then they can go and check. But the retailer can always say that, how would I know that this is right? So therefore, this is his escape route, which is why he makes the deal with fake manufacturer. So we say, put a technology like Checo, and that is definitely verified by anyone, whether it is retailer and consumer. Now, when he gets caught, he has no escape route. You can tell him, why didn't you check? Just like I'm checking, you could have checked also. Now you cannot deny. That's the point I'm making, that one has to do in order to, this kind of technology has to be made. And that's what our technology is. If you're interested, I can show you a slide on our technology.
Because I understood everything, Professor, but I did not understand how Checo technology is going to empower the consumer.
So now, then I'll go to the next slide, few slides I'll show it. So this is technology is a paradigm shift. So questions we asked ourselves is this: is the solution based on a physical feature or tag that cannot be made again? That's key question. Notice I can say, or suppose you and I are on the street and I claim to be Vijayan. I have your Aadhaar number, I have your father's name, I know your mother's name, I know your date of birth. Those are address, those are not details which are difficult to find. Somewhere you are given your Aadhaar number, so I know that details, right? Or somewhere you're given a copy of your Aadhaar card, so I have all that information. Now you and I are standing, and I am also claiming to be Vijayan, and you are also claiming to be Vijayan. I am the fake guy, you are the genuine guy. Now somebody has to determine on the street that who's genuine and who's fake. How do they do that? They can do it through your fingerprint. So your fingerprint is the unclonable ID. It's a physical feature attached to you that cannot be made again. Which is why that serves as a verifying point. And litmus test of that is, can the manufacturer, in this case, nature make that same feature again? It does not. Right? If a manufacturer like a hologram or a QR code maker, they can make the same thing again and again and again. That is therefore clonable. That kind of technology will never threaten the retailer and the nexus of retailer and the fake manufacturer. So our point is this is what we did. We said products must have a equivalent to what Aadhaar structure is. They must have a fingerprint. So we invented an ink. And we have patent both in India and US for that. And we paint that in this rectangular region. Let me pick a highlighter, a laser pointer. In this rectangular area, which you should be able to see on your screen, we paint a solid black ink. And as soon as we paint it, within tens of milliseconds, it cracks. And the white portion which you are seeing becomes visible. We painted the entire thing black, and it cracks and white portion becomes visible. What happened? Ink which was on the white portion, it climbed up, and it made it, and it made the 3D portion. It made the black portion 3D. So this is what you see. Then now notice this is like fingerprint. This is like when you are inspired by farmland. Farmland, when it dries in summer sun, it cracks. Who made those cracks? When we were born with fingerprints. Who made those fingerprints? Anything that humans make will not be a good anti-counterfeiting technology. So that means if humans have made it, they can make it again. So you have to have a technology which nature makes it or God makes it, whichever whatever which you prefer. So this is a pattern which has been made. Now, if you use a 3D printer, then printing in this integrate pattern is very, very difficult. And if you try to take a replica, you make a replica of this by taking a good scan and a print of it, then it is only 2D. Right? So in other words, you cannot make it again. And then we have put intelligence in mobile phone through an app, which is computational app. It has computer vision in it. It has artificial intelligence in it. It has image processing in it. It has cryptography in it.
Right.
And all these things then are that power has been given to consumer. You can right now go and download Checo app. It's available on iOS platform and it is available on this Android platform.
Okay.
And freely available, no questions asked, no password protection, no nothing. That app is running mathematics.
Okay.
And you can use that to verify in the field. So now you see the power has become gone into the hands of.
Yes.
So once you fix it on the on a product, and then you scan it, consumer can scan it, retailer can scan it, brand inspector can scan it, government officials can scan it, police wala can scan it, everybody can scan it. No deniability anymore.
So even if one person can do that, and it will be caught. Yeah.
Exactly. You require only one person to catch someone.
Yes. Wonderful. Totally understood, Professor. So we at what stage we are, sir, in commercializing this particular thing patent which you made?
We have transferred this technology to government security printing. We are already supplying to Indian Oil. We are supplying to HPCL. We are supplying to agriculture companies.
Yes.
And already supplying this material. There are print partners who are printing this. We maintain the app, the intelligence part in the app. That's what we do. And rest is outsourced and it's being done and it's being used by about 10 companies. And by end of this year, hopefully other 10 companies would be using it, very large companies.
So as of now, we are not using it on the currency, right, Professor?
We have discussed for the currency also, but that is always a very long,
yes.
Long
yes. Wonderful technology, sir, and I really enjoyed it, and very simplified way, the way you explained, I could understand it very well. So anything which a human can make, he can remake. So let's borrow the creativity from the nature and perfection from the nature, and that is what exactly you have done, sir. So I congratulate you on your patent, sir, and wonderful discoveries which you have made.
Thank you, Vijay.
Okay, and my next question to you, sir, is related to it was related to actually Checo TM only, but I was curious to know from where this name Checo is. This related to something checking or something?
Yeah. We wanted to make it, you're checking, but we in North India at least we use English. We speak in English, but in a Hindi sound or Hindi in English sound.
Yeah.
So check out.
Yeah.
Let's check it.
Yeah, that's good.
Let's check it. So as a let's check it. So let's check it.
Punjabi word chakko also, sir. It's a Punjabi word to pick it up.
Chuck. Okay, yes, chakko. Yeah, sure.
Okay. So, Professor, my next question to you was related to a journey of a startup, which you, I think, mentioned also, Transpax Technology. So, can you please share the success of this journey? This
success hopefully will happen. Journey never ends. It's somewhere going. It's going in good direction, but it continues. It's been 4 years, 5 years now. Some customers are on board, but it's a struggle. It's a hard struggle, and it's passion of people, not the technology. I say this to technologists all the time that we love our technology, but reality is for a startup to be success, it has to be business. It has to be business mindedness.
Yes.
And more you get engrossed in your own technology, you may make wonderful product which will not sell. And a product which is not so wonderful might sell much better. And business people have this sense. So get business people on board, respect them, and then only your startup will succeed. Don't think that as a technologist you will dominate.
That's true.
Take a back seat. As a technologist, do inventions, bring new things, solve problems, take the back seat. Give your business people the front end.
That's true. That's wonderfully explained, sir, because they are the real, people who understand whether it is going to be efficacious, workable or not. Right. So yes, you rightly said you have to respect them, bring on board and take their wisdom in developing the technologies. Very rightly said, sir. The term organic electronics is very catchy word, sir. I want you to tell something about organic electronics.
So organic electronics is natural precursor to flexible electronics. So if you look at, so as I told you that the discovery of conducting polymers had happened, and this is another story I like to tell if you have 2 minutes.
Yes.
That Nobel Prize was given to show that plastics can conduct.
Okay.
Polymers can conduct. Normally we think of plastics as insulators, right? if you want to stick your finger into a PowerPoint, probably you want to wear a plastic glove and then stick your finger in there. So they're normally considered insulators. But this discovery was shown that it could also be conducting, right? Now that conducting polymer, from commercial point of view, hasn't done much. There's some conducting application, that's about it. But in 1989, I think, in 91 time frame, from Kodak, invention was made of not conducting polymer, but taking the idea of what happens in inorganic LEDs and using a LED out of organic materials. And you see OLED TV everywhere these days, OLED screens on their mobile phones, etc. TV also. So this O stands for that organic part. That invention in 1989, which was made, which did not use much conducting polymer at all, that had very little conduction, but the device engineering allowed light to come out of it. That's an engineering product, engineered product. And that engineered product in 89-91, which Kodak showed, took us into what is called as organic electronics. And then everybody started making different kind of devices, artificial skin, this, that, and all sorts of devices could be conjured up. And so organic electronics took off from that on. And it helped that in 2000, the Nobel Prize was given for conducting polymers. Although that commercially that has not been successful. Commercially, what has been successful is not necessarily conducting, but more device engineered part of it is what made it commercially successful. But both together got this field going as organic electronics as a new field. But now you see organic are also flexible. Organics are often flexible. So that gave rise to a new world called flexible electronics. And you see these bendable phones these days. Mobile phones which are bendable. We used to talk about that in late 90s. Late 90s, we used to talk about bendable and rollable phones. Now they are reality. Take that 10, 15 years, and that is organic electronics. That organic electronics. So flexible electronics ka building block is organic electronics. Although flexible electronics has started using many non-organic, inorganic, like indium, gallium, zinc oxide semiconductor, which we have in our center, metals. All those things are also being brought in to make the full device in flexible electronics. But the mother of flexible electronics is organic device.
So flexible electronics comes from organic electronics only.
Because they were flexible,
Yes, understood.
Flexible.
Understood. Another domain of your specialization, professor, is thin film transistor, which we call TFT. Right. So traditional application of TFT is in liquid crystal displays, LCDs, what we call. We want you to, sir, please explain us the meaning of TFT and also explain the fabrication in a very, very simplified manner. So how?
Okay, organic electronics is also large area electronics, and TFT is the part of it. What do I mean by that? If you look at silicon electronics, which is high powered, which you use in computer for computations, requires switching on order of 10 to the power 10, 10 to the power 12 times per second. That's the kind of switching it requires. So it's a very, very fast device. It's made on single crystal of silicon. And silicon crystal, largest you can make these days is maybe 400 also shown, but 300 is the largest commercially shown, and most work gets done between 200 millimeter and 300 millimeter wafers, which are only this small. But if you want to make a 43-inch TV for a solar cell panel, then what do you do? Because the silicon is very small compared to that size which you wanted. So all the electronics of high performance still is done on silicon. The large area electronics, like the televisions, like organic solar cells, then switch on to some amorphous semiconductors, which is what organic semiconductors are also. So if you look at TFTs, TFTs are required for switching the pixel of the television, whether it is LCD or whether it's a OLED, does not matter for a matrix addressed display. So on the back plane, you require TFT, which essentially turns a pixel on or off, a red pixel on or off, blue pixel on or off, green pixel on or off. That's all it does. And that's why you need to. Now this circuit, TFT is a thin film transistor, is a low performance. But then for a television, if you look at, a fast moving race car, if you're looking at, a switching speed of microsecond is good enough. For most things, which we see on television, switching speed of frames switch at a speed of millisecond.
Right.
Or if you're a sports car or something fast moving objects, then okay, extreme end is microsecond. So you want low performance device done on a large area.
Okay.
Thin film transistor then is a poorer cousin of a silicon transistor in terms of device performance. In terms of current it gives very small current, and it switches at a speed which is much smaller, much lower speed, but it can be done on large area. The need fits a television, for example. Any addressable system, any system which has to switch slowly, and that's why they find their application. Otherwise, they're like transistors. Exactly like transistors. They don't have doping in the same way. They are accumulation mode devices rather than depletion mode device, or they don't have inversion concept which is associated with silicon devices. But conceptually, they are same: source, drain, gate, etc. And then you put it in a matrix address system, and in front of it you put the display, for example, or an artificial skin, or we are trying to do it for defense. Some applications we are doing using TFT, where matrix addressing is required for radars and satellite communications, etc. So all those places, those TFTs, and we are the only place in India where TFT circuits can be done.
Okay. Professor, I was going through this TFT and I found that there are some other terminologies involved associated with TFT. I want to bring to your attention those particular things, and I want you to explain those. There are a variety of techniques actually which are used to deposit semiconductors in TFT, like chemical vapor deposition, which we call CVD, atomic layer deposition, ALD, and sputtering. So can you please explain us in a simplified manner what these things are?
Sure, I can explain that, but this has nothing to do with the TFT per se. They are used in silicon technology also.
Okay.
Especially in silicon technology also, it's the same processing. Processing steps are very same as your chip manufacturing, which you do, and in TFT, these are processing steps. So CVD implies chemical vapor deposition. So if you want to, for example, deposit amorphous silicon on which you can make TFTs,
right?
How do you deposit it? So you can do physical vapor deposition like sputtering. Chemical vapor deposition means you get a precursor gas. Okay, you take a place, for example, silane. From silane, you crack it and you let the silicon deposit and all the gases come out of the chamber. On a substrate, therefore, take a glass substrate and silicon gets deposited by cracking of silane, for example, on top of the glass surface. And silicon layer forms on which you can make thin film transistor. The thin film is for that. But same thing you do for crystalline material also. Instead of glass, had you provided a silicon substrate, single crystalline, and proper conditions, then silicon atoms would have grown following the same lattice. So then they would have remained silicon, a single crystal, right? So the technology is same. And physical vapor deposition is a class, again, for many techniques. Sputtering is one of them. E-beam evaporation could be another one. Sputtering, you take a vacuum and imagine you pull a vacuum in a chamber and you have material. You take a plasma, create a plasma, energetic, and you accelerate this plasma ions and you hit the sub-target. Let's say this target is whatever you want, copper, let's say. Copper. You hit the copper and knock the copper atom out. When you knock the copper atom out, when you knock the copper atom out, you see you go to high vacuum. Why you go to high vacuum? Because you want the mean free path of this copper atom to be bigger than the dimension of the chamber. Had it not been, then this copper atom would have collided with another copper atom or some other gas material, and some mixing would have happened and something else would have happened. But because mean free path is large, that means this copper atom which is coming out goes straight in a straight line. And the other end we put a substrate, let's say glass or whatever substrate it is, silicon or whatever it is, this copper atom gets deposited there. And you deposit a layer. That's physical vapor deposition. In sputtering specifically. And similarly, you can have an E-beam source in a vacuum. Then you said ALD, atomic layer. Atomic layer deposition is like CVD, right? You use precursor gases, but do layer by layer deposition. To do layer by layer deposition, and you have a self-limiting step. Let's try to explain. Let's say you want to deposit Al2O3. right? So what you would do is on a substrate, let's say you will make a mono layer of first aluminum. Then you will pump out the aluminum source and you put oxygen source. And oxygen is self-limiting because this is aluminum layer, mono layer, so your oxygen will attach to the aluminum atoms. When it is completed the mono layer, then there is nowhere for oxygen to deposit. Now you'll pump out the oxygen in form of steam. You pump out the oxygen and you'll start aluminum again. Now aluminum, because oxygen is there, it will attach to the oxygen and make aluminum layer. And then again the oxygen layer, and layer by layer you go, and that's why it is called atomic layer deposition.
That's true. Wonderfully explained, sir, all the terms, and I could understand whatever you were explaining. And there is very, very small differences between all of these, but very clearly understood. Professor, my next question was related to fabrication. Now, electronic industry, we are undergoing transitional stage and a lot of growth in the electronic industry. Maybe this next question is related to that. So fabrication of electronic devices is extremely costly affair, and costly infrastructure is also required for that. We want you to tell us about the infrastructure part that is required to fabricate the electronic devices.
So we classify between the traditional silicon industry and what we are talking about, flexible electronics and organic electronics, etc. So let's first talk about the silicon part, which is totally commercial, and the factories are located in Taiwan, in Japan, in Korea, and some in China, and few in US and Europe, but primarily focused in Taiwan, Korea, and Japan. These are the workhorses, right? Nobody. Those cost of setting up those high-end factories is upwards of $10 billion.
Okay.
And one of them has been announced. Announcements have been in past also. Let's hope that this time it materializes. That Vedanta Group doing it in Gujarat. So that's for a display fab. So those are investments of upwards of 10 billion. Now, investment of 10 billion is by itself not important. It's like a car manufacturing. There is an ancillary system that somebody makes the gear, somebody makes the speedometer, and these ancillaries supply to a car factory, right? That means that ecosystem, surrounding ecosystem is also needed. Now, for this such a large factory of semiconductor manufacturing, you need clean water, which has a purity of 99.999%. All chemicals which are 5 nines pure, 7 9 pures, all metals, everything to be very high purity materials. There must be suppliers for that. After all, the guy who's making a chip is not going to make pure aluminum also, right? Those suppliers are pure chemicals. So those should be, the whole ecosystem also is required. And that is where it is very difficult to make them. Whereas these flexible electronics and organic electronics factories are going to be more printing based. Printing, we have expertise. They are lower cost, lower performance. They don't replace silicon technology. They complement. Certain applications get complemented so they don't compete. They work in two different domains. I told you silicon devices are high performance devices. So for computations, you'll always use silicon devices. But for things such as anti-counterfeiting, for making sensors of certain kind on body, which conform to the shape of the body, those electronics is going to be cheap electronics. Infrastructure required is much less.
Okay, so Professor, you are also in the coordinating committee of for Center for Large Area Flexible Electronics. So can you please tell us about this particular center?
This is the center I told you, National Center for Flexible Electronics.
Okay, so the same center is there. Okay.
Website is NC Flexi, Flexi FLEXE.in.
So what is the level of collaboration, sir, of industries as of now with this particular center?
Top of the head exactly, I don't remember, but there must be at least 30-40 members. Of industrial members of the center. Professor, it is meant for industry.
It is meant for industry.
The whole team is sitting, which I described earlier during the discussion with you. That's what this was center here.
So we want to also know about clean room processing and fabrication facilities that are available in IIT Kanpur.
So we use clean room of class 1,000 and then 10,000. So those clean rooms are available for fabrication. That is where we make our devices. But now I said, because we work at an industrial level, which is why we require it. But don't get worried about it. Before we started this center, all of my students used to work anyway under clean benches.
Mm-hmm.
Class 100 clean benches are available. They are not very expensive. They sit in your lab and they clean the area, the working area, small working area in which you have to work.
Okay.
And most time research is done there. So even currently our students prefer to work in our small labs under these hoods rather than gowning up for the whole day and going into the clean room, which is a lot more troublesome.
Okay.
So, but when you want your suppose you want to make a display and that there are thousands or 10,000, 50,000 TFTs on it, and you have to have all of them working, then you require a clean room because you don't want any one of them to go bad, right? Because dust particle sits and one on the bed goes bad. But when you're doing research, you will make 100. If even 10 of them work, you're fine.
That's true.
You don't worry about it. You can do measurement on those 10. You're not looking at yield. Things are meant really for yield.
That's true.
And so you can do a lot more without clean rooms, just using a simple clean bench.
Yes, yes. Wonderful. Professor, I was going through your profile and you have filed 9 patents. And
more than that, but 15, but yeah.
So I want your guidance from your side, sir, to all those who want to file the patents. Looks like it is a very costly affair, patenting, filing and patenting and all.
Okay, so I'm going to say something a little bit contrary to what you said. Yes, it's very cheap, first of all.
Okay.
It's inexpensive.
Okay.
Most of the fees is with the lawyers.
Okay.
Otherwise, as far as patent filing is concerned, with the government of India, it's a trivial sum of money.
Okay.
It's few thousand only, nothing else. And the lawyer will, for drafting it and all that, they will charge. So, etc. But practically, patent lot of things.
Okay.
But why waste money? You have an objective of patent, and I'm talking to academic world. Industrial world, reason for patent may be very different. It may be for industrial world. Let me finish the industrial world first. You may have a main patent, and what you're trying to do is patent a lot more around it, just to build a wall around the fort, so that nobody approaches your main patent. And otherwise, those patents are useless patents. That's a strategy.
Okay.
Academic world does not have to worry about that. Academic world, if you do small research, it is possible to patent it. But why would you patent it? It's waste of money. It's not expensive, but still waste of money. Patent should be done, I feel, when you actually have intent to take it forward. If you think that I'll patent it and just sell it to someone, it doesn't happen. It doesn't happen easily, and you end up losing money. That's what my experience is. Most of those patents I was excited about, but most of them have not been useful. Although I was very excited about that, they're very useful. But by alone, they don't sell easily. Few of them got licensed. But this anti-counterfeiting patent, I used it myself and converted it into a product.
Okay. Wonderful.
So academic world, don't focus too much on patent unless you feel, or you feel that I will take it to the TRL levels 5, 6, 7.
Understood.
You should do it. I think it's just got to do that. You give up very quickly. So if that is the case, then definitely patent. Then definitely.
Yeah. So 2 things came from this answer, sir. One is like contrary to what I was saying earlier, like they are costly. Actually, the cost is in only lawyer's fees and all. It is not a costly affair as far as the government fees is concerned. Second, don't file for the sake of filing.
And in India, if you want to file in US, then it can get expensive.
Then it can be. So in Indian context, don't run it only for the sake of filing. If you think that it can be commercially viable, then you should go for it.
And it will be 90% it will be commercially viable only if you make it commercially viable. If you think I've done my invention, I'm done with my job.
That is very, very nicely put, sir. And we have come to almost an end of our session. With the last question I'll ask you, and that again is a very, very interesting question for me, sir. And after interacting with you for an hour, I realized, Professor, that we have missed many things on the way, and we have a lot of things which we can catch up. In the field of production of electronic devices, if I talk about, I feel that we have not totally missed the bus. We have not totally missed all the opportunities. Still, a lot of opportunities exist. So I want a very genuine appraisal from your side, sir. Where do we stand presently in the field of manufacturing of electronic devices and all, and what opportunities we have in future for that?
So missing the bus on silicon is true. We missed it, but that should not stop us.
Okay.
For manufacturing silicon,
okay.
Having missed the bus, you can always take the next bus.
Yes.
So So that bus can always should always be tried. So if you point to understand is this, that academic world is needed where new technology is coming in.
Right, sir.
Silicon is outdated as far as materials people are concerned. So silicon is outdated. Device people can always devise new features. Okay, circuit people can continue to devise new designs. That's will always continue. That's the design side. I'm talking about silicon manufacturing and silicon. That bus has been missed for sure. But now if you want to bring manufacturing, and as government's policy is, they have given incentives for bringing manufacturing in India. Several policies have been made. This new policy is being pushed very hard, and that's what I mentioned. That requires getting a technology partner who's good at it, and having an investor from India and doing the manufacturing here. That's the fair way of doing things. That's the fair way of doing things when it is very established. Why do you want to start from scratch? Start from where the level is. But the new technologies which are coming in, that's where academic world should also get involved and should interact with industry so that we don't miss the bus on that side. And then that where when we grow as the rest of world grows, or we even exceed. National Center for Flexible Electronics attempt on that.
Wonderful, sir. So that brings us to an end of this wonderful, full of energy from your side, sir, this session. And I must thank you, Professor Deepak, for all these informations. It was a marathon session. I had almost 20 points for discussion. And along with the explanation and your presentation, sir, PPT, it was wonderfully explained. Layman like me in this particular field, I could understand. I'm very sure it is going to help thousands of students there and researchers there. And with your ideas, they will get benefited. So I wish you all the very best, sir, for your future endeavors. And I thank you once again.
And thank you, Dr. Singh, for making this effort. It was my pleasure, of course, to talk to you, to reach out to so many students. And I appreciate the effort you're making in making this happen. You are also putting huge amount of effort.
Thank you, sir. Thank you.